AI is starting to look less like a single model problem and more like a systems problem. One paper shows a foundation model built for noisy wireless telemetry can forecast and flag failures on device. Another shows you can train a competitive language model with a fraction of the usual compute, and a third turns a frozen time series model into a strong industrial prognostics engine. The real shift is that architecture, data, and deployment constraints are now driving performance as much as scale. Keep watching, because the common thread here is where AI gets cheaper, more specialized, and far more useful in the real world. Let's explore the first paper, Apex, a network native time series foundation model for forecasting and anomaly detection for wireless edge operations. Apex is a Cisco Systems network native time series foundation model built specifically for wireless edge operations, where telemetry is bursty, zero inflated, and tightly coupled across protocol layers, unlike the public corpora used by generic models. The paper trains a decoder-only patch transformer on co-collected multivariate telemetry from about 4,500 production wireless networks, covering roughly 100K AP time series with 34 metrics per AP, and uses a 1-0 channel causal chain input to predict DHCP degradation. On a 192-step, 4-day benchmark, Apex Large with 269 M parameters cuts forecasting MAE to 2.98, beating Toto's 3.64 by 18% and Sarima's 4.82 by 38%, while the 10.5M parameter Apex Edge retains strong performance with MAE 3.87. For anomaly detection, a single checkpoint with MC dropout reaches F1 equals 0.93, close to Var Mahalanobis at 0.94, and above Toto 0.85, showing that calibrated uncertainty can replace a separate detector. The Edge model is designed for AP-class hardware. Apex Edge runs in 202 milliseconds on a Raspberry Pi 5 proxy, uses only 10 5M parameters, and keeps raw telemetry on device, reducing uplink traffic from about 130 MB day to compact alerts of about KB day. The core novelty is that network-native pre-training, not just transformer architecture, closes the transfer gap for enterprise wireless forecasting and anomaly detection. Let's explore the second paper, HRM, Text-Efficient, Pre-Training Beyond Scaling. HRM-Text, from Sapient Intelligence and MIT-affiliated authors, is an existence proof that language model pre-training can be made far more sample efficient by co-designing architecture and objective rather than just scaling transformers. The paper replaces a standard decoder with a hierarchical, recurrent model that separates fast execution from slow strategic state, then stabilizes deep recurrence with magic norm and warm-up deep credit assignment. Instead of raw text causal pre-training, it trains only on instruction response pairs with a response-only conditional loss and prefix LM masking, so prompt tokens are fully bidirectional while responses remain auto-regressive. A1B. Parameter model trained from scratch on 40B unique tokens for 46 hours on 16H100S with roughly $1,472 in compute cost, reaches 60.7% on MMLU, 81.9% on ARCC, 82.2% on drop, 84.5% on GSM, 8K, and 56.2% on math. The authors report this uses about 100 to 900 times fewer training tokens and 96 to 432 times less estimated compute than comparable open models such as Llama 3.2, Qwen 3.5, Gemma 3, Olamodri, Hugin, and Uro, while preserving competitive benchmark performance. Ablations show that response-only task completion training, then prefix LM, then HRM architecture, each add gains, and effective depth analyses indicate the recurrent model maintains stronger late-layer representation change than looped transformer baselines. Let's explore the third paper, Time Series Foundation Model Embeddings for Remaining Useful Life Estimation. This paper from Friedrich Alexander Universität Erlangen-Nuremberg and Nokia Solutions and Networks shows that a frozen time series foundation model can become a strong remaining useful life estimator with minimal, task-specific training. The authors feed resampled multivariate industrial sensor windows into Chronos to extract context embeddings and train only a lightweight MLP regression head rather than fine-tuning the backbone. On two real-world Nokia device datasets, the approach outperforms linear regression, random forests, gradient boosting, GRU, LSTM, temporal CNN, and transformer baselines under the same preprocessing and chronological split protocol. For 5-step windows, it reaches MAE44 and MSE 6513 on device A and MAE64 and MSE 7212 on device B, while the strongest non-TSFM baseline remains at MAE88 on device A. The study also shows that context length is critical. Increasing the chronos, 2 lookback to 80 steps sharply improves accuracy, reducing MAE by about 2 times versus a 5-step context before saturating. And ablation confirms that the pre-trained embeddings carry most of the signal. A linear head still achieves MAE 60 on device A, while the default 2, layer MLP, is best at MAE 44, with little benefit from a deeper 4, layer head. The result is a data-efficient RUL pipeline that turns a forecasting foundation model into an industrial prognostics feature extractor. That's a wrap on today's AI paper highlights. Thanks for watching.